This question is about reactions of ions and compounds of transition metals. Part A. The flowchart shows reactions of complex ion Cu brackets H2O brackets 6 2+. Part 1. In the boxes, write down the formulae of the species responsible for the observations. This question requires you to know the colours of transition metals. This is something you need to know. It's recall in the exams and it can come up quite a lot. So if we work around the flowchart, the yellow solution would be CuCl4 2-. The pale blue precipitate is Cu brackets OH brackets 2. The deep blue solution would be square brackets Cu brackets NH3 brackets 4 brackets H2O brackets 2 2+. So square brackets are used because it's got a charge of 2+. And then the white solid is CuI, and the brown solution would be I2. So to get the 5 marks for this question, you need to get each of the boxes correct, and then for the one where it's a white solid and brown solution, you get a mark for each. Again, these are questions that test recall, so it's really important that after this question, maybe make a revision resource using all this information so you can learn for future exams how to answer a question similar to this. Part 2. Name the type of reaction for reaction 1 and reaction 2. Reaction 1, if we look at it again, is here. This is what's known as a ligand substitution reaction. It's very common with transition metal compounds in questions like this. Then reaction 2. This is known as a redox reaction. A redox reaction is where reduction and oxidation takes place. Ligand substitution is where a ligand in a transition metal compound is replaced by another. To get the 2 marks for this part of the question, you need to write ligand substitution, that's your first mark, and redox is your second mark. Part B. A hydrated nickel-2 complex A is heated in a crucible to remove the water of crystallization. The anhydrous complex B is formed. The results are shown below. The anhydrous complex B is analysed and found to have a molar mass of 309.7 grams per mole and to contain the following percentage composition by mass: nickel 18.95%, carbon 23.25%, nitrogen 27.12%, hydrogen 7.75%, and chlorine 22.93%. The anhydrous complex B contains a cation C comprising nickel, carbon, nitrogen, and hydrogen only. Cation C is 6-coordinate, contains 3 molecules of the bidentate ligand D, and exists as optical isomers. Determine the formula of A, B, C, and D, and show the 3D structures of the optical isomers of C. Show all your working. Let's start by working out the formula of the anhydrous complex B by using the percentage composition by masses and the molar mass. If we begin by working out the empirical formula of complex B, we can then compare this to the molar mass. We work out an empirical formula by taking the percentages, dividing them by the relative formula masses, and then dividing by the smallest number. So, if we work through complex B, that would be for nickel 18.95 divided by 58.7 gives us a value of 0.3228. For carbon, 23.25 divided by 12 gives us a value of 1.9375. Nitrogen, 27.12 divided by 14 gives us a value of 1.937. For hydrogen, that would be 7.75 divided by 1, which equals 7.75. And then for chlorine, 22.93 divided by 35.5 gives us a value of 0.64. The smallest number out of these is the value for nickel. So we're going to divide each of these numbers by the number or the value we worked out for nickel. So for nickel, its empirical formula, if we divide something by itself, that's going to equal 1. For carbon, dividing by 0.3228 gives us 6. For nitrogen, dividing by 0.3228 gives us 6 also. For hydrogen, 0.3228 gives us a value of 24. And finally, chlorine, dividing by 0.3228 gives us a value of 2. That makes the formula for complex B, well, it will be Ni, because it's 1 nickel, then C6, 6 carbons, N6, 6 nitrogens, H24, because there's 24 hydrogens, Cl2, because there are 2 chlorines. Next, let's work out the hydrated nickel complex A. We can do this by using the masses we've been given. Firstly, we need to work out the mass of the anhydrous complex B. We can do this by using the 2 masses I've just highlighted. So that would give us a value of 7.433, and we divide it by the relative formula mass or the molar mass which we've been given in an earlier part of the question, and this will work out the number of moles. So 309.7. That gives us a value of 0.024 moles. Then we need to work out the mass of water. So that would be using the first mass and then the 58.69 for the second mass. The difference between those masses is 0.864. We divide this by the relative formula mass of water, which is 18, and that gives us a value of 0.048 moles. So we can see it's a 1 to 2 ratio, or molar ratio, 1 to 2. That means the formula for complex A is going to be Ni C6 N6 H24 Cl2 dot H2O with a 2 in front. Next, let's work out cation C. We're told cation C is a 6-coordinate cation, and we need to focus on the formula for the anhydrous complex B to find our cation C. So looking at our formula for B, C would be removing the chlorines from the end. That makes our cation, square brackets, Ni, C6, N6, H24, square brackets, 2 plus. Because we've removed the 2 chlorines and they each have a negative charge, so it's 2 negatives, meaning the charge on the cation is 2 plus. Then the ligand, we're told it's a bidentate ligand here in the question. That means that it's going to have 2 points on its ligand that it can bond to the transition metal nickel with. That means we need to look at the part of the ion where it says C6N6H24. That would make D have the formula H2N CH2 CH2 NH2, because we're going to have 3 of these, because they're going to bond twice. And then if we've got 6 of these, it matches C6N6H24. Now let's focus on showing the 3D structures for the optical isomers of C. We need to remember that carbocation C is 6 coordinate and we've got a bidentate ligand. So if we begin by drawing our square brackets, because it's showing the optical isomers of C, and C is a cation, so it's going to be having a 2+ charge, having an ion in these square brackets. Then we're going to have nickel in the centre, our central metal ion, and then here I'm drawing a standard 6 coordinate layout 3D structure. This is something I'd recommend learning and making a revision resource of. Firstly, we're going to have NH2 joined to each of these points. So if I add them on, and we need to make sure that the nickel is bonding to the nitrogen rather than the hydrogen and nickel bonding. That is very important and something a lot of people might draw wrong in an exam question like this. Finally, we need to draw our carbon backbone, and that would be CH2, CH2. So it would look like this, with our 2 carbons here and here. So if we draw this around bonding our nitrogens together, that is the finished complex with the rest of our square brackets and our 2+ charge. The isomer, well, it would have the same basic structure of the 3D hash triangles, solid triangles, and lines. However, our carbon backbones are going to go in different positions. So again, let's start by writing our NH2 groups on each of our lines, making sure they bond, the nitrogen bonds to the nickel and not the hydrogen. This is something I'm really stressing because it's a very common mistake and something you really need to make sure that you're not the one doing it. Okay, now we're adding our carbon backbones, but they're going to go in different, or join different spaces around the complex. So to start, here, as you can see, I've kind of shifted everything round one, like a clock face. And that's a really good way of remembering this. And finally, making sure our nickels bond. Adding our 2+ charge. This is the 3D structure and the optical isomers of C. So to get the marks for this question, you need to have a comprehensive conclusion using all data to obtain correct formulae for A, B, C, and D, and a clear use of wedges in 3D structures. What this means is you've clearly used the quantitative data, you've correctly found A, B, C, and D, which we have done, and the clear use of wedges is the lines, the dotted triangles, and the solid triangles in the 3D structure, and that was something I was saying to make a revision resource out of, because it's a very common question when it comes to transition metals and the topic.